Okay, hello everyone. We'll continue our lecture on model reference adaptive control. In this piece of the lecture, we will consider a design based on Lyapunov theorem. And as you may remember, we said that we'll have a set point, say UC. This set point is applied to a reference model, and it produces the desired output, say YM. At the same time, we have the usual control loop with output Y and input to the plant U. Our purpose is to tune the controller using some adjustment mechanism so that Y would follow the reference model output YM. So now we'll consider a basic simple example to show how to use Lyapunov theorem in the design. We will consider a system with unknown gain B, and we will assume that the gain is positive, so it is known and positive. We assume that we have a reference model. The pole of the model matches the pole of the actual system, and the set point, of course, here is the input to the reference model. Now, if you assume a unit step input, we can plot here both Y and Ym. So, for example, Y would reach a steady state value of B, while Ym for a unit step input would reach a steady state value equal to 1. Both systems have the same time constant, so they reach the steady state at the same time. They have the same settling time. However, as you can see, there is a difference between Ym and Y. Now our purpose is to design a controller such that Y would follow Ym. Okay, the differential equation that represents the actual system would be Y dot minus Y plus BU, and I'm going to assume a control law which is just a simple gain controller, so it is theta. This is the gain to be adjusted and times the set point UC. The reference model equation is Ym dot equals minus Ym plus UC. I can define then the error signal as the difference between the actual output Y and the reference model Ym. And then I calculate E dot as Y dot minus Ym dot. I substitute for Y dot from the plant equation, and taking into consideration that U is theta times UC. So in that case, I can write Y dot as minus Y plus B theta times UC minus will be plus, so Ym minus UC. So this is the equation of the error. I will simplify that a little bit more, so that would be minus Y minus Ym, taking these two terms, plus B theta UC minus UC. And this can be written as minus E, where Y minus Ym is E, plus B times theta minus 1 over B all times UC. Now you can notice here that this term actually represents the error in the gain, because the gain is assumed to take the value 1 over B in order for Y to follow Ym. So normally this is in the literature referred to as phi, and phi is the error in the parameters. So when I form my Lyapunov function, our candidate Lyapunov function, it will consist of two components. One component that depends on the error between the output of the system and the output of the reference model, and the other component would depend on the error in the parameters. So that's what I did here. I have v, the candid Lyapunov function, as 1/2 e squared plus b over 2 gamma times theta minus 1 over b all squared. So this is the error in the parameters. As I said before, b over 2 gamma is just a constant, any positive constant. However, it takes some special form just for mathematical convenience. So for example, this 2 here would be cancelled out when I differentiate because of the exponent here, and b here is will appear as a common factor in the analysis, so I don't have to carry it with me in all the equations. So this is just mathematical convenience. However, you can just assume just a constant here multiplied by theta minus 1 over b all squared. Anyway, I will differentiate these, and that will give me e times e dot plus b over gamma. As I mentioned, 2 will cancel out with the exponent here. So theta minus 1 over b times theta dot. This is the equation for v dot. I will further substitute for e dot from the equation that we derived before. So we have minus e plus b times theta minus 1 over b times uc. This is e dot plus b over gamma theta minus 1 over b times theta dot. And we can write this as minus e squared plus, I will take as a common factor b times theta minus 1 over b. So what is left from the first term would be e times uc. And from the second term, I will have theta dot and gamma. Now if I look at the equation for v dot, you will notice that the first term here is negative, but this term is indefinite. Its sign can't really be determined. So we force that term to be 0 in order for v dot to be negative semi-definite. So that will require me to equate u c times e plus theta dot over gamma by 0. So I will write in that case, these two terms will cancel out, and v dot will be just minus e squared. And that will lead to the adaptation equation theta dot equals minus gamma e times uc. So this is the adaptation equation that I'd like to use. Now, this is the design. So once you calculate theta dot, which is just the multiplication of the adaptation gain by the error, which is the difference between the output of the actual system and the reference model, times the set point, you integrate that, you get the value of theta, you just multiply the value of theta by the set point, and that will produce the control signal, which is supposed to drive the output of the system to follow the reference model. Okay, once I reach the adaptation law, I can write that v dot is equal to minus e squared. So if I like to show that the system is stable, then I have to use Barbour's lemma. In that case, I have to show that v is bounded, and it is bounded above because the initial value of the output is bounded, and the initial value of the reference signal output is bounded, so that will mean that E of 0 is bounded. Also the initial value of theta will be bounded, so that means that V as a whole will be bounded. And if it is bounded from above, then it will be also bounded below, because V dot is negative semi-definite, so it is decreasing, and the lower value for V is 0. So that means that V is bounded from above and below. What's left is to show actually that V double dot is also bounded. So in that case, we have to differentiate V dot, and that will give me minus 2 E times E dot, and this is minus 2 E. I will substitute here for the value of E dot from its equation, so that will be minus E plus B theta minus 1 times UC. So that will give me 2E squared minus 2 B theta minus 1 E times UC. Now, as we agreed before, E bounded, UC is bounded also, because this is the set point, and I'm choosing the set point to be bounded. Theta is bounded because V actually is a sum of square factors. We have chosen V to be like this. It's 1/2 E squared plus the error squared in the tuning parameter. So if V is bounded, it means that every term in V has to be bounded. So E has to be bounded, and theta minus 1 over B all squared also has to be bounded. Since 1 over B is bounded, then theta has to be bounded all the time. So we have in the equation of V double dot E to bounded, theta bounded, and UC is bounded. So that means that V double dot is also bounded. And according to Barbara's lemma, that implies that V dot would go to 0. But what is V dot? V dot is minus E squared. So if that goes to 0, it implies that also E has to go to 0, and E is Y minus Ym. So if that goes to 0, it means that Y has to go to Ym. So now we have shown that actually the system is stable, and the output of the system would follow the output of the reference model. How about the estimated parameter theta? Will it go to the required value or the true value 1 over B? Actually no, there is no guarantee that will happen. Theta will go to 1 over B if some excitation condition is okay. And what we mean by an excitation condition, we mean that the signal which is used here as an input, which is in our case UC, is rich enough so that it will drive the estimation of the parameter to its true value. We'll talk about that in more detail later on. However, all what we know about theta in this example is that it will be just bounded. It will not blow up sometime during the operation of the controller. A second example that I'm going to show here actually is the case where we have a first order system. So the reference model here is first order. Ym dot equals minus am ym plus bm uc. The plant is also first order. However, we are assuming here that the parameters a and b are not known. However, again, the gain b is assumed to be of known sign, and I'm assuming it here to be positive. The control law that I'm using is a feedback controller with gain theta 2, so minus theta 2 times y, and a feed forward term which is theta 1 times uc. If we do that, we can calculate actually y dot, and y dot would be minus ay plus b times theta 1 uc minus theta 2 y. This is the equation for y dot. I will collect terms that include y together, so that would be minus a minus b theta 2 times y plus b theta 1 times uc. So this is the equation for y dot. Now I form the error equation again, so it would be minus a minus b theta 2 y plus b theta 1 uc minus the equation of the reference model, which is am plus am ym minus bm uc. Again, I will put together terms that contain y and ym. I will put minus am, y minus ym. So this part of the equation actually contains a new term, which doesn't appear in the equation of y dot, and that's minus am times y. Here we don't have that term, so I have to actually add am times y in order to leave the equation unaltered. So that would be am minus a minus b theta 2 times y plus b theta 1 minus bm uc. So this is the equation, the error equation. Now I can simplify that further as minus am times e, where y minus ym is just the error, plus am minus a minus b theta 2 y plus b theta 1 minus bm uc. I will take a candidate Lyapunov function which is 1/2 e squared plus 1 over 2 gamma b times this factor, which would correspond to the error in the parameters here, squared, and another term that represents the error in the other factor here. So this would be my candidate Lyapunov function. So I'll take the derivative of that. That will give me e times e dot plus 1 over gamma b am minus a minus b theta 2 times b theta 2 dot. This would be negative. Let's put the negative sign here. Plus 1 over gamma b theta 1 minus bm times b theta 1 dot. So now this is the equation for v dot, and again I'm going to substitute for e dot. So that would be e times minus am e plus am minus a minus b theta 2 y plus b theta 1 minus bm uc. This is the substitution for e dot, and then minus 1 over gamma am minus a minus b theta 2 times theta 2 dot plus 1 over gamma b theta 1 minus bm theta 1 dot. Now e times minus a times e, this would be negative. However, the other terms cannot be guaranteed to be negative. They have indefinite sign. So what we are going to do is to force them to be equal to 0, and that is done by forcing the term here in this term and that term to be equal to 0. So that will give me ey minus 1 over gamma theta 2 dot equal to 0, and consequently I conclude that theta dot would be just gamma times e. This will be the first adaptation law. I will also take this term together, these two terms together, to be equal to 0. So that will give me e times uc, this e plus 1 over gamma theta 1 dot equal to 0. And again that would lead to the equation theta 1 dot equals minus gamma e times uc. Once again I'm going to use Barber's lemma to show that the system output will really converge to the desired output. So we have v dot equals minus am e squared, and this is negative semi-definite. It is negative semi-definite because the error in the parameter doesn't appear in the equation for v dot, only e appears there. So the value of v dot could be 0 for non-zero value of the error in the parameters. So v dot is negative. That would lead to the conclusion that v is bounded above and below, as we discussed before. And would lead to the conclusion that e and theta will be bounded as well. So what's left is to show that v double dot is bounded. So we differentiate the equation for v dot, and that would be minus 2 am times e dot. So I'm going to substitute here for the equation of e dot. It's minus 2 am times e dot is minus ame plus am minus a minus b theta 2 times y plus b theta 1 minus bm uc. This is the equation for v double dot. Now we have E bounded, Y is bounded. Since E is equal to Y minus Ym, if Ym is bounded and E is bounded, then Y has to be bounded, so Y is also bounded. UC is bounded because this is the set point and I'm choosing it to be bounded already. Theta 1 and theta 2 are bounded because since V, the candidate Lyapunov function is bounded, then theta 1 and theta 2 have to be bounded as well. So E is bounded, Y is bounded, theta 1 and theta 2 are bounded, UC is bounded. That implies that V dot will be also bounded. And if V double dot is bounded, it means that V will go to 0, but V dot is equal to minus am E squared. So if V dot goes to 0, it means that E has to go to 0. And that implies that Y will go to Ym. So actually the output of the system will follow the reference trajectory as required. Now again, theta 1 and theta 2 will be bounded, but will converge to the true values only if the excitation conditions, and this is a condition related to the signal applied to the system, is rich enough, is able to excite the system so that they converge to the true values. So whether they converge to the true values or required values or not, still the output of the actual system will follow the output of the reference model. Now this is a summary of the controller equations. It consists of the adaptation equations, theta 1 dot and theta 2 dot, and the corresponding control signal that will be calculated based on theta 1 and theta 2. And here I have a block diagram that can be actually implemented in, say, Simulink in order to verify the operation of such a controller. Now we have a plant. That plant has an output Y, and the reference model with output Ym. The difference between these two signals is the error signal. So this is the error signal. Now I take this error signal multiplied by UC as in here. So this is the multiplication. This is UC and this is the error. So this is the multiplication. And if I multiply that by minus gamma over S, that would produce the value of theta 1. I will do similar thing for the second equation. I have E times Y. So this is E and this is Y. So this is the multiplication, and then I multiply that by gamma over S. So I integrate that, and the result would be theta 2. Now theta 2 and theta 1, I will take those into the control law. So I multiply theta 1 here by UC, and multiply theta 2 by Y, and the result here would be the control signal U, and that control signal is taken as an input to the system. So if you actually implement that in Simulink and you look at the error signal, look at the control signal and the values of theta 1 and theta 2, you would find that actually E will go to 0 and Y would follow the reference model, and theta 1 and theta 2 will remain bounded all the time. Okay, this actually completes my discussion to the implementation of an adaptive model reference controller based on Lyapunov theorem. We'll show how to implement that for more general cases in another piece of the lecture. Thank you.